Take any vector in the plane and rotate it 90 degrees. The new vector points perpendicular to the original. An eigenvector stays on its own line when a matrix acts on it. A times x equals lambda times x for some scalar lambda. But a 90-degree rotation moves every vector off its line. No real vector survives unchanged in direction, yet this rotation matrix does have eigenvalues. They're imaginary. That's the first surprise. We'll meet two ways eigenvalue analysis gets tricky. Let's find where those complex eigenvalues come from. The 90-degree counterclockwise rotation matrix Q has entries 0, -1 in the first row, and 1, 0 in the second row. Watch what it does geometrically. Take the vector 1, 1 pointing northeast. Q times 1, 1 gives -1, 1. That points northwest. A perfect 90-degree rotation. Now try 1, 0 pointing to the right. Q times 1, 0 gives 0, 1 pointing straight up. Again, 90 degrees. Every single vector lands perpendicular to where it started. No real vector maps to a scalar multiple of itself. This matrix has no real eigenvectors. Now we compute the eigenvalues. We start with the characteristic equation, the determinant of Q minus lambda, I equals 0. Q minus lambda, I is the matrix with entries negative lambda, -1 in the first row, and 1, negative lambda in the second row. The determinant is negative lambda times negative lambda minus negative 1 times 1. That simplifies to lambda squared plus 1 equals 0. So lambda squared equals -1. The solutions are lambda equals I and lambda equals -I. These are purely imaginary eigenvalues coming from a real matrix. They form a conjugate pair. If A plus BI is an eigenvalue, then A minus BI is also an eigenvalue. For real matrices, complex eigenvalues always appear as conjugate pairs. Let's verify. I plus negative, I equals 0, which matches the trace of Q, and I times negative, I equals 1, which matches the determinant of Q. Both checks pass. The rotation matrix Q is anti-symmetric, meaning its transpose equals -Q. Let's verify this. To transpose Q, we swap its rows and columns. Q equals 0, -1, 1, 0. Swapping rows and columns gives us Q transpose equals 0, 1, -1, 0. Now compare this to -Q, which is also 0, 1, -1, 0. They match exactly. Q transpose equals -Q, confirming that Q is anti-symmetric. This structure is what predicts the imaginary eigenvalues we found earlier. In fact, matrix symmetry determines eigenvalue type. There are three important cases. Case 1, symmetric matrices where A transpose equals A always have real eigenvalues. For example, the matrix 2, 1, 1, 3 is symmetric and has only real eigenvalues. Case 2, anti-symmetric matrices where A transpose equals -A always have purely imaginary eigenvalues. Our rotation matrix Q is exactly this type. Case 3, general matrices can produce eigenvalues with both real and imaginary parts. Here's the deep insight. Any matrix A can be decomposed as 1/2 times A plus A transpose plus 1/2 times A minus A transpose. That's a symmetric piece plus an anti-symmetric piece. The symmetric piece drives the real components of the eigenvalues, while the anti-symmetric piece drives the imaginary components. Complex eigenvalues are one surprise. Here's the other. First, a useful shortcut. For any triangular matrix, whether upper or lower, the eigenvalues are simply the diagonal entries. Take A equals 3, 1, 0, 3, an upper triangular matrix with 3's on the diagonal. Now compute the characteristic determinant. Minus lambda, I gives us the matrix 3 minus lambda, 1, 0, 3 minus lambda. The determinant is 3 minus lambda times 3 minus lambda minus 1 times 0. Notice that the off-diagonal product is 1 times 0, which vanishes completely. So we're left with 3 minus lambda quantity squared equals 0. Solving lambda equals 3, a repeated eigenvalue appearing with algebraic multiplicity 2. This confirms our shortcut. For a triangular matrix, the eigenvalues are just the diagonal entries. Lambda equals 3 appears twice, a repeated eigenvalue. We expect 2 independent eigenvectors. Let's check whether we actually get them. We need to solve a minus 3i times x equals the 0 vector. First, compute a minus 3i, subtract 3 from each diagonal entry. 3 minus 3 gives 0, and the off-diagonal entries stay the same. So a minus 3, I equals the matrix with entries 0, 1 in the first row, and 0, 0 in the second row. Now multiply this by the vector x1, x2. The first row gives 0 times x1 plus 1 times x2, which is just x2. The second row gives 0 times x1 plus 0 times x2, which is just 0. Setting this equal to the 0 vector, from the first row we get x2 equals 0. From the second row we get 0 equals 0. That's always true, so it gives us no information. Therefore, x1 is a free variable and x2 must be 0. Every eigenvector has the form t times the vector 1, 0. And that's one free parameter, meaning one independent eigenvector. The null space is the span of 1, 0, which has dimension 1, not 2. We needed 2 independent eigenvectors, but we only got 1. Geometrically, this matrix scales and shears. Let's see this in action. Take the vector 1, 0 pointing along the x-axis. A times 1, 0 gives 3, 0. It's scaled by 3, staying right on the x-axis. That's true eigenvector behavior. Now take 0, 1, pointing straight up. A times 0, 1 gives 1, 3. That's clearly not a scalar multiple of 0, 1. The vector got pushed sideways by that off-diagonal entry. Only vectors along the x-axis remain on their own line after transformation. Every other direction gets sheared away. This is the geometric signature of an eigenvector shortage, scaling in one direction, but a shear that ruins eigenvector status everywhere else. Now let's compare with 3 times the identity matrix. 3, 0, 0, 3. This matrix also has eigenvalue. 3 repeated twice. But 3, I times any vector equals 3 times that vector. Every direction is an eigenvector direction. The eigenspace fills the entire plane, giving us 2 independent eigenvectors, exactly as expected for a 2 by 2 matrix. Now look at the critical difference between these two matrices, the off-diagonal entry. When the off-diagonal entry is 0, as in 3i, we get a full eigenspace in the entire plane. When the off-diagonal entry is 1, as in our matrix, the eigenspace collapses to a single line, only the x-axis. A matrix that lacks a full set of independent eigenvectors is called defective. Defective matrices cannot be diagonalized. This is an important concept. Having a repeated eigenvalue does not automatically mean trouble, but having a repeated eigenvalue with too few independent eigenvectors does. Now let's step back and see the full picture. The well-behaved ideal is a symmetric matrix. It has real eigenvalues, a full set of orthogonal eigenvectors, and clean diagonalization. This is the gold standard. But 2 pathologies can depart from this ideal. The first pathology is complex eigenvalues. When a matrix has strong anti-symmetric character, meaning rotational behavior, the eigenvalues leave the real number line and appear as conjugate pairs. The second pathology is eigenvector shortage. When a repeated eigenvalue does not have enough independent eigenvectors, the matrix becomes defective and is non-diagonalizable. This is exactly what we saw with the matrix with a 3 and a 1 on the top row and a 0 and a 3 on the bottom row. But neither of these pathologies is a dead end. Complex eigenvalues naturally describe oscillations and waves in differential equations. Defective matrices lead us to Jordan normal form. a powerful generalization of diagonalization. In fact, these tricky cases host some of the richest applications in all of linear algebra. The cleanest theory assumes symmetric, well-behaved matrices. But real problems rarely cooperate, and that is precisely where true understanding begins.